So today let's talk about problem 4.1 and let's talk about A first. So now we are going to find canonical commutator relation. Okay, so what is it? So first we have to know the concept commutator. So commutator means, for example, the first one, x and y. So the commutator of x and y means we first put the x operator at the first place, then we minus yx. But how do we find the relation? We need to add a function f behind the commutator. So why do we do that? You will see the point later. So let's write it down. So xy minus yx, and both commutator apply to the function f. So we have xyf, minus yxf, and then x and y is just two variables. So there are no such things like derivative, so we can just cancel it. So it's equal to 0. So the commutator of x and y is 0. Okay, so now let's talk about the second one. How about x with py? So what is py? Py is momentum in the y direction. So they're both operator. So we apply a function f after it, and then we write it down. Okay, so what is momentum in quantum mechanics? So the momentum, we can write it down as this form. Okay, am I doing the right thing? Okay, yes. And then minus momentum. Yes, and then I have to use another comma. Then here we have x and f. So I have to write it in this way because the derivative applies to both x and f. So if I write it in another way, like del x, del y, well, it's not the same. So let's do the next step. So the x, I can write it anywhere. So just ihx. And then we keep this the same. So this is plus. And then we have to use the product rule. So here is the product rule. Okay. And x. Yes, that's right. And then because this is 0, because we're taking the derivative of y to the x, this will be 0. And the rest of the terms is just the same as the first one, but with a plus sign, so they will cancel, and it will be 0. So the commutator of x and py is 0. So let's find the third. How about x and px? So we again do the same steps, apply a function f after it, and x pxf minus xf, and they're all operator, and the operator x is just equal to x, so I can drop the operator, and then px is minus I h bar del f del x. And the right thing, we have to do the same steps. xf. Okay, I can just drop. And again, we use the product rule. Okay, so the product rule here will give me, first is f plus x del f del x. So yes, this is right. And then f plus I h bar f dx x, and then those two will cancel, which means these two will cancel. Okay, and also if you have questions about why this will become f, it's actually because f times del x, so this will become 1. So it's the product rule. I skip one step. And then we have another term, I h bar f. Okay, so we'll find that xpx commutator f is equals to I h bar f. So that means this is I h bar. Okay, so this is a very important results because we'll use a lot in this chapter and it will save us a lot of time. So let's find the fourth one, which would be, py pz. Well, let's give a try. Again, we apply a function f after it, and then we have py pz f minus pz py f. Okay, and then we write it as derivative. Okay, so the minus will be a plus, but I will write it down here. Yes, we have another minus sign here. Okay, so that means we have this. The right side will just be the, here we have a square. And also this will give us 1 because minus 1. Yeah, because I times I is minus 1 and minus plus, no, this is minus 1, sorry. Okay, and then here it will be minus. Okay, so what should we do with this and this? Well, are they the same? So here we can think that they are the same. But we have to satisfy some condition for this to be true, but I would not extend this condition here. So we can just cancel it, so it will be 0. Okay, so let's summarize our results. So x and y commutator is 0, and px, py is 0. But xpx would be I h bar. Yes, and then xpy would be 0. So what does this tell us? This means that because x, y, z are very similar, so we can extend these results to other variables like z, or any combinations of x, y, and z. So only when x commutator with px, so they are the same variable. I mean, they are not the same variable, but they involve the same variable. Like this is the momentum in x direction, and this is x. Well, they involve x. And then one has to be, well, distance, and one has to be momentum. If we have two distance, for example, we have y and z, it's going to give us 0. Or if we have x, this will also be 0 because they're both distance. We have to have one distance, one momentum, and they have to involve the same variable. For example, x and pz will be 0 because they are not the same. They don't involve the same variable. Okay. So memorizing these results can help us save a lot of time in the future calculation in chapter 4.